Biology 2121, presentation number 2, chemical level of organization. In presentation number 1, we made a brief allusion to biological organization. We said that biological things are organized into 3 basic levels: the chemical level of organization, the cellular level of organization, and the organismal level of organization. Now, to be honest with you, this course and Anatomy and Physiology 2 are going to largely deal with the organismal levels of organization, in particular the idea of tissues, organs, and organ systems. But the bottom line is you can't really truly have a good understanding of tissues, organs, and organ systems unless you understand cells. And certainly you can't have a good understanding of cells unless you have a good understanding of basic chemistry. And that's what this particular presentation is going to be about. Now, all physical matter, that is physical stuff in the universe, is made up of elements. Elements not mentioned on the slide, but I do need you to know what an element is, so make sure you jot this down. An element is a substance that cannot be broken down into simpler substances. And I think you guys know that there are plenty of substances out there that you're aware of that qualify as elements. You've heard of oxygen, you've heard of carbon, you've heard of gold, you've heard of calcium, you've heard of tin, you've heard of zinc and iron. All of these qualify as elements, substances that cannot be broken down into simpler substances. Now, the basic unit of an element is an atom, and that's what we're about to talk about here. The atom is the basic unit of an element. Now, if an element's got certain characteristics, that means the atom of that element has certain characteristics as well. So I'm looking at this illustration, and the illustration shows me a nitrogen atom, and that is the basic unit of the element nitrogen. Nitrogen is the gas that's commonly found in the air we breathe. A significant proportion of the air we breathe is nitrogen. But the fact of the matter is an individual atom of nitrogen demonstrates those very same properties. So we're going to need to understand a little bit about atoms, because if we understand a bit about atoms, we understand that atoms can actually be vehicles for storing energy, they can be vehicles for moving energy, and they can be agents of bonding atoms to one another. So technically, virtually every aspect of atoms, meaning virtually every single aspect of molecules, every single aspect of cells, leading to every single aspect of tissues, organs, organ systems, basically how we stay alive, boils down to atoms and how they interact. So that's my justification for covering this content. Now, in terms of atoms, atoms have an atomic structure. The atomic structure is ultimately composed of 3 general types of subatomic particles. Those subatomic particles are going to be located within the structure of the atom. So let's take a look at atomic structure first. Now, way back in the day, there was a guy named Niels Bohr who drew an atom to look like a little solar system. There was a nucleus in the middle, and there were little orbits around that nucleus. We're going to stick with that representation. There's more modern representations that essentially show me a little bit more accurately about the probability of where these subatomic particles might be found. But that's a little bit more intensive than we need to know right now. The solar system model that I see illustrated here is certainly adequate. So in atomic structure, we're going to have a nucleus. The nucleus is the center of the atom, and around it we're going to find little things called orbitals, or commonly called electron shells. Now, the nucleus is where we're going to find 2 of the subatomic particles mentioned below, protons and neutrons are found in the nucleus. The red balls being protons, the green balls being neutrons, and around the nucleus I'm going to find the electrons located in these orbitals or these electron shells. Now what I'm going to do is I'm going to talk a little bit about each of these subatomic particles briefly so we get a good idea of what their characteristics are and what their importance is as far as the atom is concerned. Okay, now even though the slide appears not to have changed, the illustration remains the same, but the bullet points on the left have changed. I'm going to talk about protons. Protons are those red balls found in the interior of the atom, in that region called the nucleus. Protons, as the name implies, are subatomic particles that have a positive charge. They are relatively large and they have a significant amount of mass. In other words, they weigh a bunch. Well, I guess you can't say they really weigh a bunch because this is an atom, but as far as subatomic particles are concerned, they've got a significant amount of mass. Way back in the day, there was this guy named Dalton who determined the mass of an atom, and folks named that unit of mass after him. Now, I'm not going to go into detail exactly what a Dalton is because realistically it's a very, very, very small number. It's a fraction, an itty-bitty fraction of a gram. But I just need you to know that every single proton in the nucleus weighs 1 Dalton. To be honest with you, that is going to contribute to the overall density of the atom. But then again, I should also say that the number of protons that are found in the atom's nucleus is going to determine the identity of that atom. If you took a look at the periodic table of the elements, some of you guys have had chemistry courses in the past. Periodic table of the elements is nothing more than a table that arranges the different elements in tabular form. But the fact of the matter is every single atom has a number, and that number is called the atomic number. And the atomic number is equal to the number of protons that are found in the atom. This is something you need to know. A proton is a positively charged entity. It's a positively charged subatomic particle. It has a mass of 1 Dalton, and the number of protons in an atom determines the identity of that atom. So if I count the number of protons in this picture of nitrogen, I see 1, 2, 3, 4, 5, 6, 7 different red balls. One of them you can't see because it's tucked behind the others, but 7 protons means this particular element, nitrogen, has an atomic number of 7. If this was an illustration of an atom of carbon, I would see 6 protons. If it was an illustration of an atom of hydrogen, I would find 1. The number of protons is the atomic number, is the identity of the atom. Let's talk about neutrons. Neutrons are also located in the nucleus. They're represented by the green balls here. And as a rule of thumb, and there are exceptions to this, but as a rule of thumb, in most atoms in nature, the number of neutrons will equal the number of protons. We'll mention an exception to this in a moment. So you remember protons are pretty darn critical because they determine the atomic number, which in turn determines the identity of the atom. Well, it turns out that I got the same number of neutrons in many cases. Now, neutrons differ from protons in the sense they have a neutral charge. They have the same mass, that is a mass of 1 Dalton. So the number of neutrons and the number of protons essentially contribute to the overall mass of the atom, ultimately results in the density of the material. But the fact of the matter is this idea that the number of neutrons equals the number of protons, I said, was fairly common in most atoms occurring in nature. The exception are atoms that are commonly referred to as isotopes. Now, an isotope, you'll need to know this, an isotope is an atom that has a different number of neutrons. That is, a number of neutrons that's not quite expected. Think about carbon. I'm going to mention carbon very briefly here. Don't have a picture of it, but I can talk about it. Carbon is an atom that has 6 protons and 6 neutrons. And so therefore, the common occurring atom of carbon is called carbon-12. 6 protons plus 6 neutrons equals 12. So carbon-12 is the most commonly occurring form of carbon in nature. However, very, very rarely you might find a carbon atom that has 7 neutrons. If you got 7 neutrons and 6 protons, that gives you carbon-13. So carbon-13 is an isotope of carbon. Sometimes you wind up having an atom of carbon that has 8 neutrons. 6 protons plus 8 neutrons gives us carbon-14. That's an isotope of carbon as well. Now, one other comment here. You'll notice the next bullet says that these isotopes can be radioactive. As a matter of fact, if an isotope is radioactive, that means a couple of things. Number one, it means that the atom is relatively unstable. In other words, it's going to degrade or decay over time. Now, that degradation or decay generally involves item number 2, which is the release of radioactivity. Hence, isotopes that are radioisotopes are radioactive and give off some degree of radioactivity. Now, I mentioned carbon-14 a second ago, and carbon-14 is an example of a radioisotope. Now, I gotta mention the fact that a lot of times we associate radioactivity with things that are very, very dangerous, and that is so. But does not mean that radioisotopes do not have application for helpful things. So in the field of medicine, there is an area that is called nuclear medicine, and nuclear medicine uses radioisotopes for the purposes of diagnosing and visualizing and understanding certain aspects of medicine. So if you're at all interested, you could just go ahead and Google nuclear medicine and see what you come up with. But I need you to know neutrons are one of those subatomic particles. They have a neutral charge. They weigh 1 Dalton. They're located in the nucleus of the atom. As a rule, number of neutrons equals the number of protons. If there's some difference, that's called an isotope, and isotopes can be radioactive. What about electrons? Electrons are our 3rd subatomic particle, and they're quite a bit different from the other 2. Electrons have a negative charge. You take a look at the illustration, we notice they are located in orbitals around the nucleus of the atom. Their mass is negligible. They're so small that their mass is going to be many orders of magnitude less than that of our protons or our neutrons. Now, another rule of thumb. In nature, generally, and there are exceptions to this, there's always exceptions, but as a rule of thumb, the number of electrons in an atom will equal the number of protons. That makes for an electrically neutral atom, which is inherently stable. So if I'm thinking about carbon, and I mentioned carbon before, carbon has 6 electrons. Carbon in nature, as a rule, has 6 neutrons. Hence, it's called carbon-12. But in addition, I should mention that carbon has 6 electrons. Having 6 electrons is essentially what makes carbon electrically neutral, because the 6 electrons, which each have a negative charge, balance out the positive charges of the protons. Now, the exception is occasionally you will find an atom that has an extra electron, or an atom that has 1 or 2 electrons less. And if you got extra or missing electrons, you are called an ion. Now, an ion is a charged atom. Make sure you write that down somewhere in your notes at this point. An ion is a charged atom. That means it's an atom that's got a charge on it. That charge might be positive, it might be negative. It might be 2 positives, it might be 3 positives, it might be 2 negatives, it might be 3 negatives, but it all boils down to if that atom has extra electrons, in which case it would have negative charge, or less electrons, in which case it would have a positive charge. We'll be talking more about ions in a minute. Just remember that ions are charged atoms, atoms that have gained or lost electrons. Now, electrons are going to be important because they can be energized. An electron can be a vehicle for storing energy and can be a vehicle for moving energy. So if I took a look, for example, at a molecule of glucose, which is a sugar. It's a common sugar that we find in our bloodstream. It's C6H12O6. And that molecule glucose is constructed of atoms of carbon and hydrogen and oxygen. They're all bonded together. But the electrons in those atoms are energized, which means if the electrons are energized, the whole shooting match, the whole molecule of glucose contains stored energy. And when you and I break down that glucose molecule in our individual cells through a process called cellular respiration, which you may have encountered at some point in your past, when you break down that glucose molecule, you liberate those energized electrons, and you can use that energy in turn to make this stuff called ATP, which is cellular fuel. Well, the other thing that's really, really important about electrons is not only can they store energy, but they can participate in bonding. If you've got 2 atoms and they're going to interact, it could be a hydrogen interacting with an oxygen. It could be a sodium interacting with a chlorine. It could be carbons interacting with hydrogens and oxygens. In any event, those atoms bond to one another. They establish linkages. They establish connections. And so the fact of the matter is, you think about it, and then you look at the picture there, you're seeing the fact that these electrons are in the outermost regions of that atom. If that nitrogen was to bump into a hydrogen, or maybe 3 hydrogens, it would actually create some bonds between itself and those 3 hydrogens. That would create something called ammonia, which is NH3. But the fact of the matter is the bonds are created by the interactions of the electrons. Because when you think about it, if the electrons are on the outermost edges of the atom, when that atom bumps into another, that's where you're going to get the bonds forming between them. So at this point, we've kind of done I'm not going to say exhaustive, but a pretty complete review of the subatomic particles. Make sure you know what protons are, neutrons are, and electrons are, and their characteristics, and all the possible variations that are included. Our current slide, more about electrons 1, is going to reinforce some content that I alluded to on our last slide. I'm going to give you some extra information as well. We understand that electrons can be gained or lost, and the result of gaining or losing an electron is going to create an ion or a charged atom. So let's take a look at our illustration over here. You will see a couple of atoms illustrated at upper right. One's sodium atom and one's a chlorine atom. And what we're going to see is that when we join sodium and chlorine together, we get a compound called sodium chloride. Sodium chloride is what you and I know as common table salt. It's not salt per se, it is common table salt, because I will tell you this, when you create a linkage between 2 atoms, like I see here with sodium chloride, and one atom loses an electron and one atom gains an electron, that's called an ionic bond, and that compound is called an ionic compound. And ionic compounds are commonly called salts. This is something you're going to need to know because it's something that's going to crop up in your future education, and it will crop up in your future career. So somewhere on your notes, you write down the word salt, S-A-L-T, and write an equal sign, and you write down ionic compound. You see, sodium chloride is the one we're most familiar with. However, there's all kinds of salts out there. Calcium chloride qualifies as a salt. Potassium iodide is a salt. Copper sulfate is a salt. Salts are ionically bonded compounds. Sodium chloride is just one example. Now, if you take a look at the illustration at right, you will see the phrase ionic bond up there, and you'll see sodium in orange, and you'll see chlorine in green. If you take a quick look at the sodium, you'll see one teeny tiny little ball in the outermost orbit. That's one electron. You will see that sodium loses that electron, and the electron travels to chlorine, which picks it up. And so therefore, the bond that is formed is a result of the loss of an electron by sodium and the gain of that electron by chlorine. But what's important here is that fact that when that sodium loses its electron, it becomes an ion. It becomes a positively charged atom. You see, it's losing a negative charge, so it becomes more positive. Chlorine, on the other hand, becomes an ion also. And chlorine becomes an ion because it gains that negative charge. It becomes a negatively charged ion. So what we're going to do is we're going to learn there are some names that we put on these ions to identify them as either being positively charged or negatively charged. You will need to know these terms as well. So an ion, yes, is a charged atom. A cation is a positively charged atom. It is an atom that has lost an electron. An anion is a negatively charged atom, and it has gained an electron. Now, should also mention that while atoms can lose and gain electrons, should understand that molecules are able to lose and gain electrons as well. And when a molecule loses an electron or gains an electron, there's some terminology that goes along with it, and we can actually use that same terminology to describe what's going on with our electrons. So there's two words. Dr. Kness, there's an awful lot of terms here. Well, yeah, there's an awful lot of terms. I can't help that. That's the nature of the beast. And you will need to know those terms. And speaking from experience, yes, it's going to be important in the short term, but it's also going to be terribly, terribly important in the long term. So we've got terms. Ion, we've got cation, we've got anion. Got two more here. One term is the word oxidation. Now, oxidation is a term that applies to a loss of an electron. So when sodium loses its electron to chlorine, that's an event of oxidation. We can say that sodium becomes oxidized. So oxidation is a process by which an electron is lost, and therefore the atom or the molecule that loses that electron is said to have been oxidized. The other term is the word reduction. And reduction means a process of gaining an electron. Well, Dr. Kness is kind of counterintuitive. I mean, the word reduction sounds to me like I'm losing something. But you're telling me that reduction is gaining an electron. Well, you think about it this way. If the electron has a negative charge and you're gaining an electron, your charge is becoming reduced. You're losing charge. Your charge is becoming more negative because you've gained that electron. That's the idea. So reduction is a process by which we gain electrons and become more negative. Oxidation creates cations. Reduction creates anions. And you got to understand that those two same terms can apply to molecules. Molecules can gain and lose electrons as well. Now take a look at the illustration right at the bottom. These reactions, oxidation reactions and reduction reactions, are always coupled. That means they always occur together. You can't have one occurring without another. And so a lot of times, folks who are in the know will refer to these coupled reactions as redox reactions. This is a very cool way of referring to a reduction reaction and an oxidation reaction that occur as a pair. And the reason why they cannot occur without each other is if you lose an electron, it's got to go somewhere. And if you gain an electron, it's got to come from somewhere. You can't have one without the other. And in many cases, we have substances that actually encourage this process of oxidation and reduction. So we've got things that we could call oxidation agents, or we've got things that we call reducing agents. An oxidizing agent is going to encourage the loss of electrons from another molecule. A reducing agent is going to encourage the gain of electrons by another molecule. Know these terms: ions, cations, anions, oxidation, reduction, oxidizing agent, and reducing agent. Now, this whole idea of gaining and losing electrons is going to have application to how we can move energy from place to place in the cell. And this is going to be important. For example, later on in the semester, we're going to talk about muscle contraction. And in understanding muscle contraction, we will understand that you have to be able to have a source of energy to accomplish muscle contraction. And that source of energy ultimately comes from food molecules, which are going to be broken down, and we're going to remove the energized electrons from those food molecules and generate something called ATP. Got to understand the process, cellular respiration, to understand how we're going to be able to fuel this process of muscle contraction, which incidentally is critical for you to do a really good job in this particular course. And I promise you it will have application in the future. So let's start with what we already acknowledged. We know that electrons can be energized, and I can move those electrons around. It's what I would call energy transfer. And that energy transfer can be accomplished through redox reactions. And remember, those are those coupled reactions I just talked about. Now, our classic example is cellular respiration. The reason why we call it cellular respiration is because it occurs in every single one of our cells. It's how we break down food molecules and liberate the energized electrons, and we ultimately make ATP. The process of cellular respiration is going to involve also oxygen and carbon dioxide. It's one of the reasons why we call it cellular respiration. Because when we think of respiration, we generally think of bringing in oxygen and putting out carbon dioxide, which is what happens at the level of our bodies. That's what happens when we breathe. But the reason we breathe is to deliver that oxygen to our cells, and the carbon dioxide we produce is the waste product that we get from breaking down the food molecules in our individual cells. Now, take a look at the slide. You'll see glucose, the far left. That's a food molecule. C6H12O6. 6 carbons, 12 hydrogens, 6 oxygens, but a whole bunch of energized electrons. And I'm going to break apart that glucose, and I'm going to transfer those electrons to water. In a nutshell, follow the red arrow. the electrons are going to be used to take that oxygen and convert it into water. At that point, water is a waste product. But take a look at what I'm going to do with those electrons before they get to water. Those electrons are energized. I'm removing them from the glucose molecule, so the glucose molecule is being oxidized. As a matter of fact, I don't have that on the slide, but go ahead and write that off to the side. Glucose is being oxidized, because what I'm doing is I'm cleaving apart that glucose molecule. I'm getting out the electrons. Now watch the yellow arrow. What I'm going to do is I'm going to use the energy from those electrons to make this stuff called ATP, which is cellular fuel. If you want to make something, to break something, to move something, to transform something, anything that you do in a cell that is an energy-intensive process, ATP is the fuel molecule that we need. It's the same molecule that I'm going to use to contract those muscle cells that I talked about not too long ago. So cellular respiration is a process by which food molecules are oxidized. Glucose is our example here. Glucose is not the only food molecule on the face of the planet. Any carbohydrate, any protein, any fat can function as a food molecule. It's just that glucose is our convenient poster child for how a food molecule ought to behave. So my slide here shows me that through the process of oxidation, I can transfer energy in the form of energized electrons ultimately to water, but I can use that energy to generate ATP in the process. Electrons can be energized, they can be used as vehicles for moving that energy, and I can do so through redox reactions. In this case, the glucose is being oxidized, but you think about it, the oxygen, which is gaining the electron to make water, is being reduced. You can't have an oxidation reaction without a reduction reaction. That's why I refer to them as redox reactions overall. All right, we're going to switch gears a little bit. We're going to now talk about atomic bonds. There are three basic types of atomic bonds, and on the next 3 slides, we will take a look at those. Now, our first slide is going to talk about an atomic bond that actually has relevance to the topic that we just finished talking about. We're going to talk about ionic bonds. Ionic bonds are one type of atomic bond. It's how we create a linkage between 2 atoms. And you're already an expert in this, at least from the standpoint that you know that you can take an atom of sodium, transfer an electron from the atom of sodium to an atom of chlorine, and establish a bond between the two. That bond is called an ionic bond. So if you look at a slide, ionic bonds are bonds where electrons are gained and lost. Therefore, ionic bonds are formed through a redox reaction between atoms. One atom is reduced, one atom is oxidized. In the case of sodium chloride, and it's illustrated there a little bit differently from what I saw before, but it's the same basic idea. Sodium becomes oxidized, chlorine becomes reduced. And the result is an ionic compound, which we call a salt. And I'll let you guys know that salts are compounds that are commonly also referred to as electrolytes. That's a nutrition type term. Most of you guys have heard the word electrolytes in terms of things like Gatorade and Powerade and things like that. And if you sweat a lot during exercise, you need to replace your electrolytes. Well, the reason why these compounds are called electrolytes is because they're charged. A long, long time ago, scientists realized that they could actually conduct electricity. So electrolytes were thought to be materials that are dissolved in water that could easily conduct electricity, and it turns out they are these ionic compounds, atoms that have either positive or negative charges. So as a rule of thumb, when you take a look at a salt, when you take a look at an ionic compound, when you take a look at an electrolyte, it consists of 2 constituent parts. One part is the cation, and the cation is a positively charged atom. And the other part is called an anion, which is the negatively charged atom. Obviously, the cation loses the electron, anion gains the electron. Sometimes it might be more than one electron, but the bottom line is you have this negative positive relationship. Now, the other thing I want to mention here is the anion sometimes can be what we call a polyanion, which means the negative constituent of this salt might be more than just one atom. Take a look at the compound to immediate right of the word polyanion. You'll see CaCO3. That's calcium carbonate. And you'll see the illustration of it. The blue is the calcium, the carbonate is the carbon, which is the red, and the oxygens, which are the three greens. The bottom line is the calcium has a positive charge on it. It functions as the cation, but the carbonate, which is the combination of the carbon and the three oxygens, itself has a negative charge. So we still have ourselves an ionic compound. We still have charged atoms. It's just that the charged atom, on terms of the negative constituency, consists of multiple atoms, and that's what we call a polyanion. Now, a little bit more content here. When we take a look at ionic compounds, because they have a negative charge and a positive charge, they are commonly referred to as polar compounds. And when you have a polar compound, the one important thing to remember is polar compounds, as a rule, are water soluble. It means they can dissolve in water. And that's of practical importance for you guys to understand that when you have this blood that is circulating through your circulatory system, and it's carrying oxygen, and it's carrying nutrients, but it's also carrying other things that are dissolved in that blood plasma, and those are ionic compounds or salts. Because they're charged, they're attracted and attractive to water, and we'll talk more about that a little bit later, but they are, as a rule, soluble. They can dissolve in water. Now, later on in our semester, we'll learn that ions can be used to create charge differences across membranes. So if you got a whole bunch of positive charges on one side of the membrane, a whole bunch of negative charges on the other side of the membrane, that creates a charge difference. That's a voltage difference. That's what's called a voltage potential. If you take a look at the lower right, you'll see a kind of a generalized view of a nerve cell. That funky looking thing in blue is a nerve cell. And the close-up view, follow the arrow, shows you charge differences on the outside versus the inside of that nerve cell. Now, believe it or not, this is something you're going to become intimately aware of later on this semester. So I don't feel badly about showing it to you guys right now. But when our neurons, our nerve cells, do their job, they start off with this charge difference. They're always positive on the outside and always negative on the inside. That's called a voltage potential. If I am going to send some information down that neuron, for example, it's going to travel from the left to the right. That bit of information is going to travel as a wave of charge. So I can't have a wave of charge travel down a neuron unless I already have a voltage potential existing. So just tuck that in the back of your mind. You can understand that these ions are going to be critical to the establishment of voltage potentials across membranes. And that's going to have relevance when we talk about nerves. It's also going to have relevance when we talk about muscles. And that's not too far off in the future. Okay, we're done with ionic bonds. Bonds that occur when electrons are gained or lost. Now we're going to turn our attention to covalent bonds, bonds that are created when electrons are shared. And those electrons can be shared equally or they can be shared unequally. So let's take a look at the illustration at right. Unfortunately, this is not in your PowerPoint presentation that's posted on D2L because I just decided to add the illustration at the last minute. Just make sure that you're aware of the fact that the illustration does exist. Or you could conceivably Google polar covalent bond or non-polar covalent bond and come up with virtually the same illustration or any number of versions of the same illustration. But here's what I need you to know. A covalent bond is a bond in which electrons are shared between atoms. So the atom doesn't lose its electrons and it doesn't gain electrons. Now, if those electrons are shared equally, that result is what we're going to call a non-polar covalent bond. Look at the illustration at right, go to the bottom. It says non-polar covalent bond. Now, there's a lot of stuff on this illustration, but I just want to concentrate on the two atoms. You'll see atom A covalently bonded to atom A, and you'll see the electrons being shared equally between the two, as exemplified by the equidistance between those nuclei with respect to those electrons. Now, because the electrons are negatively charged, there is a negative charge here, but the fact of the matter is if the atom on the left and the atom on the right are sharing those electrons equally, neither atom becomes more positive nor more negative. So you'll notice when I say over here that sometimes electrons can be shared equally, that is called a non-polar covalent bond because there is no distribution of charge. Nothing negative, nothing positive. Now, because there is no charge, no negatives, no positives, as a rule, nonpolar substances do not dissolve in water. So, for example, salad oil is a good example of a nonpolar substance. Any fat, any wax, these are nonpolar substances. They are sometimes described as being hydrophobic or water-hating for the simple reason that they don't have those positives or negatives that would allow them to become attracted to water and allow them to dissolve. Now, on the other hand, sometimes these electrons can be shared unequally, in which case you've got what's called a polar covalent bond. Now, Dr. Canals, I assume that means that one atom is going to have a greater pull on those electrons. And if those electrons are negatively charged, I would imagine, Dr. Canals, if you have a greater attraction for those electrons, you will have a more negative charge. Whereas the other atom is not pulling so hard on those electrons, it's going to have a more positive charge. So let's take a look at the illustration at right at top. And it says polar covalent bond. I've got atom A, I've got atom B. But what I notice is it looks like B has a greater attraction for those electrons than atom A. And you'll see this funky little Greek letter, which is like a delta, indicating to me that the charge difference is slight. It's not big. It's not like a plus or a negative as far as cations and ions are concerned. But what it is you see there is a slightly more negative charge for B because it's more attracted to those electrons, and a slight positive charge for A because it's less attracted to those electrons. But the bottom line is because you have those positive and negative charges, it does make this compound attracted and attractive to water. So when you share the electrons unequally, you get a polar covalent bond, meaning you do have a distribution of charge, positives and negatives, and because they're positive and negatives, this would qualify as a polar substance, and it therefore is going to be hydrophilic or water-loving. It is going to dissolve in water. Now, fact of the matter is these things that we're going to call covalent bonds are characteristic of all biological molecules. To be more specific, I can say they're characteristic of all food molecules. So it doesn't matter whether you're talking about a sugar, which is a carbohydrate, or you're talking about a protein, or you're talking about a fat, they all have covalent bonds. Now, as a rule, the carbohydrates are going to have polar covalent bonds. The fats are going to have non-polar covalent bonds. And the far majority of proteins will have polar covalent bonds as well. But the bonds that I find in molecules are going to have an awful lot to do with how that molecule is going to function. And not only how it's going to function, but how it's going to behave. So, for example, if I take a look at your bloodstream, or you look at your own bloodstream or the bloodstream of a patient in your hearts of hearts, you know that that bloodstream is going to feature sugar molecules that are dissolved and being transported through that bloodstream. There's going to be proteins that are dissolved and being transported through that bloodstream. And there are going to be salts that are dissolved and being transported through that bloodstream by virtue of the fact that every single one of those compounds are polar. They have little positives, little negatives, and they're attracted to water molecules. On the other hand, you don't find fats dissolved and being transported in your bloodstream. Later on in Anatomy and Physiology 2, hopefully you will encounter the way your blood actually does transport fats. They don't dissolve, but they're packaged as little itty-bitty, teeny-tiny little particles called chylomicrons that are then transported to the blood. So instead of having to rely on solubility, because you can't, fats don't dissolve. You package them in these little transportable particles and they travel to your individual cells, and when they arrive at your individual cell, they are unloaded of their contents. So it's a little bit different way that you transport things, but on practical level, what is polar and what is non-polar has an awful lot to do with how you transport things around your body. So we've been through ionic bonds and we've been through covalent bonds. And one thing I can say with absolute surety is that both ionic and covalent bonds involve electrons directly. Now we're going to turn our attention to a third atomic bond type, and this one, the hydrogen bond, is different because electrons are not directly involved. What's a hydrogen bond? A hydrogen bond is a weak electromagnetic attraction between oppositely charged entities. If you ever played with magnets when you were a kid, you know that the positive pole is attracted to the negative pole. That's an electromagnetic attraction. Take a look at the illustration top right. See a water molecule. Now, a water molecule is H2O. And the hydrogens are bonded to the oxygen through polar covalent bonds. We just talked about that. So if you take a look at the water molecule, you'll see there's a little bit of a positive charge on each of the hydrogens and negative charge on the oxygen. See, the deal is the oxygen has a much greater pull on the electrons than the hydrogens. Hence, water is a polar compound. It's one of the reasons why water is really, really good at dissolving polar things. But the bottom line is I want to focus on these positive and negative charges on the water molecule. Those are not electrons directly. They are caused by the unequal sharing of electrons in the molecule. But let's take a look at how water actually behaves. Illustration at far right. I see 1, 2, 3, 4, 5 water molecules, and I see little dotted lines connecting between them, and those dotted lines are hydrogen bonds, weak electromagnetic attractions. If you look very carefully, you will notice that it is the negatively charged oxygen that is attracted to the positively charged hydrogens and vice versa. So water molecules tend to be attracted to each other in this magnetic fashion. These attractions are hydrogen bonds, often results from an interaction between polar covalently bonded molecules. Examples: water molecules are hydrogen bonded to one another. I see that at the top. Water molecules can cause polar compounds to dissolve. I notice in that little blue inset at right a crystal of sodium chloride. The sodiums are green, the chlorines are gray, and I notice that essentially the water molecules are clustered around those atoms to break apart the molecule of sodium chloride. Lastly, water molecules can cause salts to dissolve or other compounds as well. So for example, you see at the bottom right a big fat protein. Now, ordinarily proteins aren't so terribly soluble, except for the fact that a protein is covered with lots of little positive and negative charges. And those little positive and negative charges make that protein molecule attracted and attractive to water molecules. So hydrogen bonds, like I said, are weak electromagnetic attractions. They're responsible for water molecules sticking to each other. They're really also responsible for water molecules sticking to other things. So for example, if you go out in the rain, the reason you get wet is because the water molecules are sticking to the little positive and negative charges in your clothing and on your skin. And then finally, those hydrogen bonds are critical to the process of dissolving substances in water. So at this point, make sure you have a very clear idea of what are ionic bonds, what are covalent bonds, and what are hydrogen bonds. We've been talking about bonds. The first two types, ionic and covalent bonds in particular, are formed as a consequence of chemical reactions. We already mentioned chemical reactions thus far: oxidations, reductions, the fact that certain compounds dissolve in water. Those are examples of reactions. What's a reaction? Interaction between molecules and or atoms that create bonds or break bonds. And as a rule, chemical reaction will involve reactants and products. And a little arrow in between the reactants on the left and the products on the right is called a yields arrow. Reactions involved in the making and breaking of molecules, and I'm going to need you to know the four basic types of chemical reactions. They are listed below. They're illustrated at right. They are mentioned in your textbook, and you can certainly Google every single one and get a more clear idea of what's involved. In any event, any reaction, be it a synthesis reaction, a degradation reaction, a single replacement reaction, or a double replacement reaction, involves reactants on the left and products on the right. Now, there's two additional terms on this slide I need you to know. I see the word anabolic reaction and I see the word catabolic reaction. The word anabolic comes from the word anabolism, which means to make. An anabolic reaction makes something. Anabolism is a synthetic reaction. It makes something. On the other hand, degradation or decomposition is a process where we break something apart. The process of breaking down glucose, the oxidation of glucose, is a catabolic reaction. So catabolism or catabolic reactions are the flip side of anabolism or anabolic reactions. Make sure you're clear on those terms. Now, there's one more very important aspect of chemical reactions we're going to mention at this point. It might not have application in this semester, but it definitely will have application next semester when you start talking about the digestive system and how the digestive system breaks down things like starches and proteins. And also, it's relevant to how we make certain molecules, how we make our own proteins, for example, or how we synthesize our own nucleic acids when we make DNA in anticipation of cell division. What am I talking about? I'm going to be talking about reactions involved in the making and breaking of polymers. Well, what's a polymer, Dr. Knaus? All right, take a look at the box at right. A polymer is a long chain molecule. It's nothing more than a molecule composed of repeating units that are called monomers. So for example, and I wish I had put a picture of it here, but for example, go ahead and Google starch. Go ahead and Google molecular structure of starch. And you'll see that starch is nothing more than a really long molecule of repeating glucose units. Individual glucose molecules link together into long chains. So a polymer is a long chain molecule composed of individual units called monomers. And in the world of biology, in the world of human biology, some of the most important polymers are starch. I just mentioned that, important component of our diets. Proteins, technically, are polymers. Glycogen, which is how we store energy in our own bodies, in our muscle tissue, and in our livers, those are examples of polymers. Now, polymers can be made and polymers can be broken. And the making of a polymer is called a condensation reaction. And you'll see it illustrated at right below. Its partner reaction is hydrolysis, which is the breaking of a polymer. Now, the deal is, if I want to make a polymer, I need to create a bond between two monomers. If I want to break a polymer, I need to break that bond. And it turns out that water is going to be critical to this process. Take a look at the illustration at right, and let's take a look at a condensation reaction. The condensation reaction in this case is going to start with two molecules of glucose. You'll see a little inset, it says the number 2 glucose, and you'll see them illustrated there. One glucose on the left and one glucose on the right. Now, if you look carefully, you'll see that those two glucose molecules are not linked. However, what I've done is I have highlighted a hydrogen on one glucose molecule and an OH group or a hydroxyl group on the other glucose. I highlighted those. Now, the reason why I highlighted those is when you put a hydrogen and a hydroxyl or OH together, you get H2O. So what I'm going to do is I'm going to link those two glucose molecules, and in the process, I'm going to create a molecule of water. That's what we're going to call a condensation reaction. Now, sometimes condensation reactions are also called dehydration synthesis reactions. Synthesis, because what we're doing is we're creating a bond where there was not one previously. I remove the hydrogen, I remove the OH, and I create a brand spanking new linkage between those two locations. Dehydration, because as I remove the hydrogen from one glucose molecule and as I remove the OH group from the other glucose molecule, I am technically removing a molecule of water. Condensation reaction, also called a dehydration synthesis reaction, removes water and makes a bond. It's how I make a polymer. Hydrolysis reaction, I'm going to do the opposite. Start off with maltose down below. Now, maltose is what we made when we linked those two glucose molecules together. But now take a look at maltose. You'll see a funky looking bond linking those two glucose units. I want to break that. And water is going to be my agent to do that. That's why I call this hydrolysis. Hydro implies water. Lysis means to break. But what I see is if I throw a water molecule at that bond, I break the bond and I wind up right back to where I started off with. Glucose on the left, glucose on the right, and hydrogen on the left, an OH group on the right, two separate and distinct molecules. I added water and I broke the bond. Make sure that you equate hydrolysis with breaking. Make sure you equate condensation with making. and understand that it's the agent of water is involved in the making or the breaking of bonds in polymers. As long as we're on the topic of chemical reactions, let's talk about chemical reactions that involve energy. Now, some of the content on this slide, the content at the top, is going to be brand spanking new. Content on the bottom is just going to be nothing more than a review. Here's what I need you to know. A reaction that is a chemical reaction that consumes energy is called an endergonic reaction. Take a look at the illustration at right. You will see a reaction that shows you a purple line, reactants on the left, products on the right, and you'll see that the reactants are a lot less energized than the products. The products have significantly more energy than the reactants. The way that happens is the reaction adds energy to those reactants. In other words, the reaction consumes energy to get to the products. That's why the products are more highly energized. That's an endergonic reaction, a reaction that consumes energy. The flip side of that coin are exergonic reactions. If you take a look at the illustration at left, you'll see the reactants are a lot more energized than the products. If I'm going to convert those highly energized reactants on the left to much less energized products on the right, I am going to be releasing energy, and that's an exergonic reaction. An exergonic reaction is a reaction that releases energy. Now, below you see reactions involving electrons, and remember those electrons can in fact be energized. We talked about oxidation reactions and reduction reactions, and so that should be no issue. Now, a lot of times we start messing around with charged atoms. We can use the word ionization to describe things that go on. So let's take a look at, for example, water. Okay, now I know that water isn't going to represent our typical ions, but watch what happens here. Water is H2O, and I see it there at the bottom left. I'm going to take that H2O molecule and I'm going to break it apart. When I break apart the water molecule, I can call that ionization. Why do you call that ionization, Dr. Knauss? Well, because when I break that water molecule apart, I liberate a hydrogen atom that has a positive charge. It's missing an electron. And I create an OH group, which is called a hydroxyl ion, because it has a negative charge. When I break water apart, I get a positively charged hydrogen ion, and I get a negatively charged hydroxyl ion. That is ionization. Technically, if I broke apart sodium chloride, I'd be doing the same thing. I create ions as a consequence. In fact, the matter is, if I wind up breaking apart this molecule because it contains electrons, those electrons, either released or gained, can represent energy, either released or gained. Now, folks, most of the reactions that keep us alive are too darn expensive to occur naturally. What do you mean too expensive, Dr. Knauss? I mean, they're too energetically expensive. When you think about it, if you go to an automobile dealership and you want to buy a car, that car is probably going to be financially improbable. I mean, I've got expensive taste, and I'll go to a dealership, and the first car I look at is like well over $100,000. I want that car. I can't buy that car. I can't buy that car to save my life. And literally, in the world of biology, most of the reactions that keep us alive, we can't possibly afford. So somehow we manage to get those reactions to happen so we can stay alive. Well, how do we do that? Well, in the case of buying the car, the only way I could buy the car would be if the dealer would give me a substantial, and I mean substantial, discount. And the same thing happens in a lot of these biological reactions that keep us alive. Those biological reactions need to have some kind of discount, and that discount is going to be provided by something called an enzyme. So let's talk about enzymatic reactions. An enzymatic reaction is a reaction that involves the interaction of a substance called an enzyme. And we're going to find out what an enzyme actually does. Take a look at the illustration at right. And you'll see a graph, and you don't want your eyes to roll back in your head. You see reaction process going across the bottom from left to right. That's basically time. I see a conversion of reactants to products. That's no-brainer. And on the left, I see the amount of energy that must be present. My reactants have a certain amount of energy. My products have a certain amount of energy. But if you look at the graph, you'll see a really, really tall red hill between reactants and products. That red hill represents the amount of energy that must be present for that reaction to occur on its own. That's what we call activation energy. So you could go ahead and circle activation energy on the left and write down the amount of energy necessary for a reaction to proceed on its own. And in this case, it's a significant amount of energy. Now, to be honest with you, I can't afford that. You cannot afford that. Your cells cannot afford that. So you will see that particular big, tall, red hill is labeled without enzyme. But Dr. Kanish, you said we could get a discount. Well, let's take a look at the blue line now. And the blue line shows me the hill is not anywhere near as tall. And it says with enzyme. So what an enzyme does is it lowers activation energy. It makes an improbable reaction possible. Now, in the words of enzymes and enzymatic reactions, reactants are commonly called substrates. And the reason they're called substrates is because the enzyme acts on them. As a rule, the enzyme is a protein, just a really, really, really big molecule. And it's got a special shape. And that special shape allows it to bind with those reactants. Take a look at the illustration bottom left, and you'll see the enzyme is that big red shape. And that big red shape looks like it's got a specific place on it that meets the substrate or the reactant perfectly. And it's going to break those reactants apart. So reactants are commonly referred to as substrates. You still get products, and the whole point of the enzymatic reaction is to use that enzyme to lower activation energy. Enzymes are very specific. One enzyme won't do a lot of different jobs. For example, in our own bodies, there is an enzyme called amylase, and what amylase does is it breaks down starch. That's all it does. It does nothing else. Enzymes are very specific, and one of the reasons they're very specific is that active site that I just mentioned, that I see illustrated at the bottom left, has to specifically match those reactants. Now, when the enzyme binds to those substrates, you get something very, very temporary that's very, very critical, and you'll see it in the middle of that illustration, bottom left. And that thing in the middle, bottom left, is labeled there as enzyme substrate complex. And I want you to know three things about the enzyme substrate complex. Number one, it is a perfect fit between the enzyme and the substrates. It is a perfect fit between the enzymes and the substrates. Number two, the enzyme substrate complex is temporary. It's temporary. It only lasts as long as needed. And number three, perhaps the most important, is the enzyme substrate complex is where the activation energy is actually lowered. So the enzyme substrate complex actually makes the reaction possible. So enzymes make energetically improbable reactions possible. And to be honest with you, probably a good 99.999% of all the reactions taking place in your cells every day, 24/7, that keep you alive are enzymatic reactions. Because there's no way you and I could generate enough energy to stay alive if it weren't for enzymes. Let's shift gears one more time. Let's talk about the chemistry of water. Water is arguably one of the most important substances on the face of the planet. It's important as far as we're concerned. We're anywhere from 50 to 70% water. Our water content is significant. Why? Well, because water is the medium in which all these chemical reactions that take place in our cells that keep us alive, incidentally, occurs. All of our reactions are aqueous reactions. In other words, they occur in aqueous or water solution. So let's talk about water. Water is a polar compound. Why? Because we mentioned before that the hydrogens bond to the oxygen through polar covalent bonds. That means water's got what's called a dipole nature. One end of the water molecule is positive and one end is negative. The hydrogens are positive, the oxygen is negative. And the great thing about those positive and negatives is water tends to make hydrogen bonds, and hydrogen bonds to itself. We say that water has cohesive properties. You take a look at the young lady sipping water out of that red Solo cup. The water rises through the straw in an unbroken column because of hydrogen bonding. If I was to look at the surface of a pond and I saw a water strider on top of that pond, I see a boat floating on that pond. In my heart of hearts, I know there's surface tension there. And that surface tension is because the water molecules are attracted to each other at the water's surface. Water tends to stick to other things. Things get wet, like the dude who's just come out of the swimming pool. And that is testimony to the fact that not only can water molecules stick to each other, but they can stick to other things. And then we say water is adhesive. Cohesive, water sticks to itself. Adhesive, water sticks to other things. Water is an effective solvent. It dissolves things by virtue of the fact that it is polar. The little positives and little negatives on the water molecule tends to wedge itself in between positive and negative parts of molecules or atoms. Is one of the reasons why water dissolves salt real well. It's one of the reasons why water dissolves sugars real well. Water tends to resist changes in temperature. It has what's called a high specific heat. And this has an awful lot to do with its hydrogen bonds. Most of you realize that you can drive by a pond or dive into a swimming pool on a particular day, and water temperature might be 75 in that swimming pool, and air temperature might be in the high 80s. But let's suppose all of a sudden air temperature in the next couple of days goes up to 104. Oh, that swimming pool looks really, really good, Canals. I think I'm going to jump in. Well, you jump in that swimming pool and you thank the Lord that that swimming pool is not 104 degrees like the air temperature, because you would scald yourself. Instead, you jump into that swimming pool and it's really not much warmer than it was a few days ago. And one of the reasons is because water resists changes in temperature. It has a high specific heat. And we benefit from that because our own bodies being 50 to 70% water, we don't experience the fluctuations of temperature that we might, simply because water buffers those temperature changes. So water absorbs energy to keep us cool, technically. And in another respect, you'll see water absorbs energy to evaporate. So not only does water actually store energy and absorb heat energy, it uses up energy when it evaporates. And you think about it, one of the reasons why a water molecule is able to technically lift off from its liquid form into a water vapor form is because you wind up breaking hydrogen bonds to do that. When water evaporates, you apply heat energy, and that heat energy breaks the hydrogen bonds, which allows those molecules to leave the liquid water and become water vapor. But the great thing about that for us is when we perspire, and it's a really, really hot day, we experience something called evaporative cooling, because as those water molecules evaporate from our body surface, they take energy right with them. And it's one of the things that contributes to our being able to cool down. Every single one of you is familiar with the fact that if you get sweaty and you stand in front of a fan, it doesn't even matter if that fan is blowing hot air on you, you still feel cool. And the reason you feel cool is as those water molecules are leaving your body surface, they're taking heat energy with them. Make sure you know these aspects of the chemistry and behavior of water summarized on this slide. Y'all probably have heard of pH before. pH is a measure of something. It occurs on a scale of 0 to 14. It's a measure of how acidic something is or how basic something is. Inherently, you probably realize there's acids at one end of the scale and bases at the other end of the scale. But our job is to find out exactly what pH is. Because obviously, if I'm concerned about health, for example, I'd like to make sure that my blood pH is at the level it needs to be. If it goes too low, I'm going to be sick. I could die. If it goes too high, I'm going to be sick. I could die. So let's understand what pH is about. It says here on my slide that pH is a quantitative measure of the amount of hydrogen ion concentration in a solution. If I look at a swimming pool, that swimming pool has a certain pH. If I pour myself a glass of lemonade, that lemonade has a certain pH. The contents of my stomach have a certain pH. The plasma in my blood has a certain pH. And that pH is a measure of how much hydrogen ion is in that glass of lemonade, in that swimming pool, in my blood. pH is based on the dissociation of water. I'm not going to go into a tremendous amount of detail, but if you look at the illustration at the bottom of the slide, you will see that when water dissociates, and we used the word ionize before, when water comes apart, it creates hydrogen ions and it creates hydroxyl ions. And if you're talking about the dissociation of pure water, the dissociation of pure water results in the equal amounts of hydrogens and hydroxyls. Well, the fact of the matter is, if pH exists on a scale of 0 to 14 and pure water dissociates, that means I have an equal concentration hydrogen ion on one hand and hydroxyl groups on the other. That would technically give me a pH of 7, smack dab in the middle. So water is our standard for pH, and the pH of pure water is pH 7 because it gives me exactly equal amounts of hydrogens and hydroxides resulting from the dissociation of water. But now let's take a look at what constitutes acids and bases and how they reflect on this pH scale. Okay, if the pH scale is 0 to 14, acids fall on the low end and bases fall on the high end. You remember pH of 7 is neutral. Acids 0 to 7, bases 7 to 14. Now, the fact of the matter is acids, as a rule, are high in hydrogen concentration. Acids have lots of hydrogen ions. Now, the thing is, it's counterintuitive that if you have a high hydrogen concentration, you would have a low pH value. I'm not going to go into details as far as the math is concerned. There is some weird little algebraic equation that results in the formulation of the pH number. But you simply just need to know if the pH number is low, then the hydrogen ion concentration is high. If the pH number is low, then the hydrogen ion concentration is high. And the flip side is true of those bases over there. What is basic, or sometimes the term alkaline is used. What is basic is something that has fewer hydrogen ions. But if you got fewer hydrogen ions, your pH number is high. So once again, it's counterintuitive. If the pH value was high, then the hydrogen ion concentration is low. So make sure you're straight with that. The relative number of what is a pH measurement indicates really roughly how much hydrogen ions are there. If the number is low, there's lots of them. If the number is high, there's much fewer. Let's qualify the differences between acids and bases without going into a whole lot of detail. Acids, as a rule, are electrolytes. Remember, those are compounds that have charged atoms. These are electrolytes that release positively charged hydrogen ions. Now, a positively charged hydrogen atom is sometimes called a proton. Very simply, it's a hydrogen atom that has no electrons, so it's only got a proton. So if you've got an acid and you pour it into a swimming pool, for example, what the acid will do is release its hydrogen ions. It will release its protons. It is called a proton donor. Taking a look at the illustration below, you'll see hydrochloric acid at left, and that's a strong acid. And when you pour that into water, it dissociates into hydrogen ions and chloride ions, which means in a swimming pool, if you were to dump a gallon of hydrochloric acid in there, hydrogen ion concentration would go up, which means as hydrogen ion concentration goes up, pH number goes down. So electrolytes that release hydrogen ions are called acids. They're considered to be proton donors, and they generally are characterized by having a pH of less than 7. So what about bases, Dr. Canals? Let's focus on the second bullet point first. Bases are considered to be proton acceptors. An acid is a proton donor. A base is a proton acceptor. You see, if a base accepts protons, it's going to accept positively charged hydrogen atoms. And as it accepts those positively charged hydrogen atoms, the concentration of hydrogen ions in solution will decrease. And as the hydrogen ion concentration goes down, pH value goes up. How do bases do this? Well, let's take a look at the first bullet point now. Bases are electrolytes that release hydroxyl ions. What's a hydroxyl ion? It's an OH negative. The thing is if you got something that's an OH negative, what is it going to bind to? Well, hydrogen comes to mind. If you're OH negative and there's hydrogens bouncing around, you're going to bind to the hydrogens and you're going to make water. In other words, a base is designed to remove hydrogens from solution. That's what the OH group does. That's what the hydroxyl group does. Look at the illustration at the bottom of the slide. I see sodium hydroxide over there, NaOH. That is a base. One of the reasons why it screams out to me that it's a base is I see the OH group there, the hydroxyl group. And notice that in solution, it will dissociate in the sodium and OH. Well, the fact of the matter is that OH group, the hydroxyl group, is going to be accepting free hydrogen ions in solution. And as it does so, that OH group will be transitioning into water, and the amount of hydrogens will be going down. As the amount of hydrogens go down, the pH value goes up. So what happens when an acid and a base react? Well, it's kind of nifty. When an acid and a base react, what we get is a salt, something that we're already familiar with. Sometimes these are called neutralization reactions because when an acid reacts with a base, both are neutralized pH-wise, and what they produce, the salt, is not reflected on the pH scale. It has no pH value whatsoever. So let's take a look at an example. Here I've got hydrochloric acid on the left, sodium hydroxide, a base, and I react them, and I'm going to get water because the OH group on the sodium hydroxide accepts the hydrogens from the hydrochloric acid, and what I got left is the sodium from the base and the chlorine from the acid. I'm going to hook them up, and I'm going to make the salt. And I know that salt, sodium chloride, has no hydrogens, has no hydroxyls, and therefore has nothing to do with pH. So make sure you know acid-base reactions always, always, always results in a salt. And they qualify as neutralization reactions because the salt has no pH at all. And the neutralization comes to the fact that the acid is being neutralized by reacting with the base, and the base is being neutralized in reacting with the acid. Now, this last slide deals with something that we could refer to as pH homeostasis. Homeostasis, Homeostasis, maintenance of a constant internal environment. I might have mentioned that in presentation number 1. I don't remember. We'll mention it again if we haven't. But the fact of the matter is homeostasis is maintaining a constant internal environment, and we do that as far as body temperature is concerned, but we also can do it as far as pH is concerned. And it's pretty darn important because pH variations, having too many hydrogens, having too few hydrogens, can really mess up these reactions that are taking place in our cells. So we need some way of being able to make sure that pH is maintained at some constant value in our bodies. And that mechanism is carried out by substances called buffers. Buffers are substances that resist changes in pH. And they kind of function like a teeter-totter over there. You see that if you sit on one end of the teeter-totter, that will go down, the other end will go up. What buffers do is they seek to balance between those two extremes. What would be acids on one side and what would be bases on the other. So how does a buffer actually do this? Well, I see the second line on my slide says that buffers function like a proton reservoir. What's a reservoir? Well, where I grew up in Philadelphia, we had these big giant reservoirs in the city. And it's generally where we got our drinking water from if the Delaware River got too darn low. Because if the Delaware River got too darn low, the salt line from the Atlantic Ocean would start coming up through the Delaware Bay, up the Delaware River basin, and we'd have to get our water from somewhere else because otherwise it would be too salty. So we had these big, giant, concrete lined, it almost looked like massive swimming pools where they would store all this water. And so if water supplies dropped low, you'd access water from the reservoir. If our water supplies got high, you put the extra water in the reservoir. So the reservoir is your way of being able to supply you with water if you needed it, or a place to store water if you had extra. And the same thing happens with a buffer. Instead of thinking about water, we're thinking about hydrogen ions. If I've got too many hydrogen ions in solution, now understand, if I got too many hydrogen ions in solution, my pH number is low. I want to bring that back up. Because if my pH number is too low, I could get sick, I could die. So the buffer, in turn, would actually absorb some of those hydrogen ions, store them, and that way reducing the hydrogen concentration in solution and bringing pH value back up. On the other hand, maybe my pH value would go up and I need to have more hydrogen ions to make things work better, so my buffer would do the same thing. Take some of those extra hydrogens and release it. So buffers resist abrupt and large swings pH in the body, particularly our bodily fluids like our blood plasma, by releasing hydrogen ions when pH begin to rise, and also binding hydrogen ions and removing them from solution when pH begins to fall. Now, the chemical equations below are not necessary to memorize. I would never ask you them before. All they're doing is they're trying to show you the process of releasing protons and removing protons in order to maintain pH balance. All I care about is that you know that buffers are substances that resist changes in pH, and they're critical for pH homeostasis in the body. Dr. Knaus, haven't we been doing chemistry long enough? Well, we've been through the basics. It's now time to get into organic chemistry, which is the chemistry of biomolecules. We talk about carbohydrates and proteins and fats and nucleic acids. Those all qualify as biomolecules. Those all qualify as organic compounds. So what makes for an organic compound? Well, these molecules, as a rule, are pretty darn big, and they are basically constructions of carbon atoms that are covalently bonded to one another. And some of these compounds are polar covalently bonded, as in the carbohydrates and many of the proteins, but in some of them, they're nonpolar covalent bonds. For example, the fats. So covalently bonded carbon atoms are arranged into a carbon skeleton. You take a look at the bottom of this slide. On the left-hand side, I see an amino acid. Amino acids are the building blocks of proteins. But in a nutshell, if you take a look at that amino acid, you will see a central carbon, and you'll see a carbon immediately to the right. That is what constitutes the carbon skeleton. In a carbohydrate like glucose, that carbon skeleton might be 6 carbons long. In others, it might be even longer. Now, on that carbon skeleton, we're going to find things called functional groups. In our illustration below, the oval on the left highlights a functional group, something that we'll call an amino group, and on the right, a functional group that we would call a carboxyl or an acid group. This is an amino acid. Gets its name from those two functional groups. Now, the functional groups can sometimes be real simple, like maybe a simple oxygen and a hydrogen, or a lot more complicated. It could be a phosphorus and 4 oxygens. But the bottom line is the functional group is nothing more than a small arrangement of atoms that confer properties on the overall molecule. So, yeah, the basics of the molecule are those 2 carbons smack dab in the middle, but it's the functional groups, the amino group on the left and the carboxyl group on the right, that confer properties on the overall molecule. Now, the other thing about biological molecules, and we kind of made this observation before, is they are oftentimes really, really, really long chain molecules that we'll call them polymers. And those polymers are composed of individual units called monomers, technically individual molecules that are linked together to form the polymer. And we made the observation that it is a process of a dehydration synthesis, also known as a condensation reaction, that results in the formation of those linkages. Conversely, we can break the linkages through hydrolysis. So organic chemistry is the chemistry of biomolecules. Let's see where that takes us. Well, I guess the first place we head is to actually identify these functional groups. There are basically 7 different types of functional groups in the world of organic chemistry. We are only going to identify 4 of them. These are the ones that are most commonly encountered. The hydroxyl group, which you see over there on the right in our illustration of ethanol, which is an OH group. The amino group, which we mentioned in the context of the amino acid, which is an NH2, a nitrogen and 2 hydrogens. An acid group, or more officially known as carboxyl group, which is a carbon double bonded to an oxygen and single bonded to a hydroxyl group. I see that on the right. And then finally a phosphate group, which is characteristic of probably one of the most important molecules we'll encounter this semester, ATP. So in each of these cases, I've got a small arrangement of atoms that confer properties on the overall molecule. Ethanol behaves the way it does because of the hydroxyl group. The amino acid behaves the way it does because of the amino group and the carboxyl group. And ATP behaves because it does by virtue of that phosphate group that I see. As a matter of fact, there's 3 of them. It's always nice to review, and this slide is basically a review of the fact that polymers can be made, polymers can be broken. I don't feel compelled to go into the great detail, except you see a dehydration synthesis, aka a condensation reaction illustrated on the left, and hydrolysis reaction illustrated on the right. Dehydration makes a bond, hydrolysis breaks it. And in both cases, water is involved. So once again, you're going to need to make sure that you are very much in control of what is the process that makes a polymer and what is the process that breaks it. The world of organic chemistry is really, really big. There are a lot of different compounds that qualify as organic compounds. And a lot of these are man-made things. Now, in this particular course, we're not going to get into the organic solvents, and we're not going to get into the plastics. But plastics and organic solvents and a whole host of other compounds qualify as organic compounds because of the simple fact that they are ultimately composed of covalently bonded carbon atoms. In the world of biology, we're going to limit ourselves to 4 of those classes: the carbohydrates, the lipids, the proteins, and the nucleic acids. You have heard of every single one of these. So in a nutshell, carbohydrates are sugars, starch, glycogen, fiber that we find in the foods we eat. Lipids include fats and oils, and cholesterol, and sterols, and waxes. You've heard of proteins before. Nucleic acids are DNA and RNA. Every single one of these classes are characteristic of living organisms, and every single one of these classes are composed of covalently bonded carbon atoms, and those carbon atoms are arranged in a certain manner, creating a carbon skeleton, and they all have their unique and very specific functional groups that confer properties on those molecules. And every single one of them have specific structures and specific jobs to do. And we're going to cover those in just a moment. Let's talk about carbohydrates. What do you need to know? Carbohydrates include compounds that we commonly call sugars. Sometimes we call them polysaccharides, which would imply a long chain molecule made up of sugars linked together, which would include starch in plants and our diet, and glycogen in humans and other animals, and fiber. Carbohydrates all have the same basic atomic composition. They're all made up of carbon, hydrogen, and oxygen. That's it. Always in a 1 to 2 to 1 ratio. So therefore, if I take a look at glucose over there, I see it's C6H12O6, which means I got 6 atoms of carbon, 12 atoms of hydrogen, 6 atoms of oxygen. And the same would be true for any carbohydrate. Always in a ratio of 1 carbon to 2 hydrogens to 1 oxygen. Now, most of the carbohydrates that we encounter in biology are water soluble. The only exception are there are some fiber compounds that are not water soluble. Carbohydrates tend to be our body's preferred short-term source of calories because the calories are easily accessible. It doesn't take a lot of energy to break down a molecule of glucose, whereas it takes a little bit more effort to break down a fat molecule, or it takes a whole lot of effort to break down a protein molecule. Now, we take a look at human populations across the planet. Starch is the primary source of calories for most populations on the face of the planet. Some of our more poor, let's say less developed nations, their populations sometimes derive as many as 70 to 80% of their calories from starch. In the case of folks in the United States, it's probably about 50%. The unfortunate thing about us is instead of getting those calories from complex carbohydrates, we get them from refined sugars. And so you take a course in nutrition, you'll figure out exactly what that issue is all about. Now, in human beings, glycogen is actually the way we store energy. Plants store energy as starch, and we eat that starch. Humans, animals, store energy in the form of glycogen. Glycogen is nothing more than a long chain molecule of glucose, just like starch is. They're very, very similar in terms of their composition. So where do we find glycogen in human beings? Two places. We find it in the liver. If you are running around with excess blood sugar after you've eaten a meal, what will happen is that excess blood sugar gets removed from the bloodstream by the liver and is used to create glycogen. And the glycogen is a means of storing that glucose until you might need it. So for example, when you're laying in the bed at night and you're asleep, even though you're asleep, your cells still need a source of glucose. You've not eaten. And so therefore, there's going to be a point in the middle of the night where your cells start screaming, we need glucose. You're not going to wake up. But what your liver is going to do is your liver is going to deconstruct that glycogen that has stored. We'll also find glycogen in muscle tissue. Now, the great thing about glycogen in muscle tissue is it is a ready source of energy for muscle contraction. It's like a built-in energy source right in your muscle tissue, at which point all you have to do is deconstruct the glycogen, get the glucose, put it through cellular respiration, get ATP, fuel the contraction. There's no fuss, no bother. In order to contract your muscles, you don't have to sit down and eat a meal and wait for the meal to digest and wait for the molecules to travel to your cells and wait for the cellular respiration to take place. It can all happen right then and there in muscle tissue. Surely you didn't think I was not going to make you know some types of carbohydrates. So here it goes. We mentioned glucose. Glucose is the number one carbohydrate, the number one sugar found in all of biology. I can't imagine there is a single living organism on the face of the planet, ranging all the way from bacteria all the way up to animals, that do not have glucose present in some way, shape, or form. So glucose is that hexagonal molecule I see on the left. I'm not going to ever ask you to memorize that structure. You'll just need to know that it is C6H12O6 and that it is a really, really common and very important molecule in biology. Now, its neighbor right next door is called fructose, and it looks a little bit different. It has a pentagonal shape. But I'll tell you what, if you looked at the chemical structure of fructose and count up the carbons and count up the hydrogens and count up the oxygens, you'll get the exact same chemical formula. Glucose is C6H12O6, and so is fructose. Fructose is C6H12O6. Now, we got a name for molecules that look differently but have the same chemical formula. They're called isomers, I-S-O-M-E-R-S. Now, not to be outdone, fructose and glucose have another isomer around, and it's called galactose. Galactose is seen over there on the far right. Galactose hardly ever occurs in nature as a single monosaccharide molecule. In other words, it hardly ever exists in the form that we see it there. But more commonly, it does exist in a form that we call lactose. And you'll see lactose below, which is milk sugar. Regardless, you will need to know there are 3 major monosaccharides that you need to be aware of, and they all have the chemical formula C6H12O6. They're isomers, and they're found in very specific combinations and in very specific molecules. Let's see what that's all about. Go down the list. Monosaccharides are glucose, fructose, and galactose. You'll need to know those. And then we've got disaccharides, maltose, sucrose, and lactose, and you'll need to know those. Disaccharides are 2-unit sugars. Monosaccharides are single-unit sugars. Mono means 1, di means 2, saccharide means sugar. So if you take a look at the illustrations below, you'll see maltose on the left, sucrose in the middle, and lactose on the right. In each of the cases, you see there's 2 monosaccharides linked together. Now, the linkage between the monosaccharides is a special type of bond. I need you to write this down. It might be on the next slide. I can't remember. But the linkage that you see between the 2 glucose molecules in maltose, between the glucose and the fructose in sucrose, and between the glucose and the galactose in the lactose molecule at the right, that funky little bond that has the oxygen in the middle of it is called a glycosidic bond. That's spelled Glycosidic, a glycosidic bond. Glycosidic bonds are bonds that link monosaccharides together. And you'll need to know that maltose is a linkage of 2 glucose molecules. It's a disaccharide. Sucrose, aka common table sugar that you're all very, very familiar with, is a glucose molecule linked to a fructose molecule with a glycosidic bond. That's a disaccharide. And then finally, lactose, also known as milk sugar, is a glucose glycosidically bonded to a galactose molecule. Now, carbohydrates are not just limited to monosaccharides and disaccharides, so let's talk about polysaccharides, and then we'll talk about oligosaccharides, and then we'll wrap up with fiber. Polysaccharides are long-chain molecules, and the big 3, I guess maybe I could call them the big biological 3, starch, glycogen, and cellulose, are all polymers of glucose. They look a little bit different. If you look at the illustration at right, you'll see starch is actually a composition of 2 different molecules, amylose and amylopectin. You'll see glycogen, and then you'll see cellulose. There's not a whole lot of difference between starch and glycogen, except the fact that starch is a mixture of amylose and amylopectin, but those are glucose-based polymers, and so is glycogen. And they're relatively highly branched in each case. If you take a look at cellulose, those molecules are long-chain molecules, but they're unbranched. Cellulose provides a function for plants as a structural molecule. It's what the cell walls are made of. So polysaccharides, there's a bunch of them out there, right? But as far as the biological big 3 are concerned, you need to know starch, which is how plants store energy, glycogen, which is how animals store energy, and cellulose, which is a structural molecule for plants. Technically, cellulose is actually a form of fiber as well, so you might want to draw a little bitty arrow from cellulose all the way down to the last major bullet point there that says fiber. And matter of fact, draw it to the word insoluble, because cellulose does not dissolve. When you eat plants, a great deal of that plant material travels right through your intestinal tract and never gets digested and never gets absorbed. And it contributes to fecal bulk and material as it leaves your digestive tract. Let's turn our attention to oligosaccharides. Oligosaccharides are short chain polymers. They're nowhere near as long as polysaccharides, starch, glycogen, and cellulose. If you take a look at the little yellow highlighted illustration at right, and once again, I would never ask you to memorize these, but you'll see these oligosaccharides, and the prefix oligo means few. Basically, these are chains of a few sugars, and they create compounds that are known by some rather strange names. One is called raffinose and another called stachyose. There are a few others, but these are the ones that you encounter on a daily basis. Well, when do I encounter them, Dr. Knaus? Well, oligosaccharides are characteristic of beans, and they're characteristic of things like cabbage and broccoli and Brussels sprouts, and every single one of those food items I've just mentioned generate a certain degree of, let's be delicate here, let's say flatulence. They create gas. See, one of the problems is we don't have an adequate way of breaking down these things, but bacteria love them. And when bacteria break down oligosaccharides, they will generate methane as a consequence, which ultimately results in flatulence. So when you go to the store and you buy a product like Beano, which is nothing more than an enzyme that aids you in the breakdown of raffinose or stachyose, so these oligosaccharides, so that you don't make that gas, which can be, let's put it, a bit embarrassing on occasion. Okay, now finally, there is a class of carbohydrates that we refer to as fiber. Fiber is generally structural compounds found in plant materials. And so when you eat a stick of celery and you notice the stringy things in the stalk of celery, or you're eating green beans and you see these stringy fibers, that's fiber. Now, cellulose is the number one fiber, but there's other fiber compounds that very, very close to the structure, that is the chemical structure of wood. Now, you and I can't digest wood. Not many organisms are capable of digesting wood. As a matter of fact, even termites are not capable of digesting wood. They have teeny tiny little protozoans living in their guts, and those protozoans, those little single-celled organisms, are capable of breaking down wood. If the termite didn't have the protozoans, the termite would not be able to make a living. Now, fiber comes in two different types. There's the soluble fiber and there's insoluble fiber. The basic difference between the two is soluble fiber tends to absorb water. Insoluble fiber, on the other hand, does not. If you've ever gone to the store or watched TV and see advertisements for a product called Metamucil or Citracel, these are essentially fiber preparations that you can take to actually improve intestinal motility. That's just a nice way of helping you move fecal material through your large intestine. And what this material is something called psyllium husk, which is a plant material that they grind up, and it absorbs water. And when it absorbs water, it forms this big, bulky, gel-like material that aids in the movement of material through your large intestine. It makes it a lot easier to pass that fecal material. But then again, there is plenty of plant material that includes fiber that does not absorb water, but still contributes to bulk of the stool as it passes through your large intestine. So we're done with carbohydrates. Let's take a look at lipids. Lipids are a pretty big category of compounds. And if you take a look at the list down there, I see triglycerides, phospholipids, sterols, fatty acids, and eicosanoids. And of those compounds, the ones you're most familiar with are going to be the triglycerides, which are fats and oils. But the one thing that all of these compounds have in common is their high molecular weight, non-polar molecules. That means they're big, they've got a lot of atoms, but those atoms are linked by non-polar covalent bonds, which means, as a rule, they are not water soluble. They don't dissolve in water. If you would, you might want to write down the word hydrophobic on this slide. They're not polymers, only a group of organic molecules that aren't polymers. Many carbohydrates are polymers, proteins are polymers, nucleic acids are polymers, but lipids are not. Despite the fact as big as they are not long chain molecules. Then they generally play a role in long-term energy storage. That's their main metabolic role, although a lot of times lipids will play a role in insulating. They will play a role in protecting. They will play a role in thermal insulation. We will bump into these alternative functions as we progress through this course and as you progress through anatomy and physiology too. So let's take a look at these individual categories of lipids. Well, if I take a look at lipids, I'm going to realize they do have a chemical structure. I am not going to go into tremendous detail. There are some very important things you'll need to know, though. So while I'm not going to ask you to memorize the chemical structures here, there are some things I will point out. First off, triglycerides are the most common group of lipids that you and I encounter. They're what we commonly call fats and oils. Fats are part of our biology. Fats and oils are part of our diet. So these compounds called triglycerides get that name because they are three something bonded to something else. So what do you mean, Canals? Take a look at the schematic at right. You'll see something there, a vertical box labeled as glycerol. Glycerol is a 3-carbon molecule. On that glycerol, you will see 3 fatty acids. They're arranged vertically. So the triglyceride almost looks like capital letter E. And I've got a glycerol molecule and I have 3 fatty acids. You will need to know that triglycerides have that same basic composition. Now, the fatty acids can vary. What's a fatty acid? Well, a fatty acid is a really, really long hydrocarbon chain. There's nothing more than a long chain of carbons with a bunch of hydrogens around it. So if you take a look at the illustration, yeah, you see lots of carbons and you see lots of hydrogens. As a matter of fact, take a close look at the 2 featured fatty acids in the middle of those illustrations on this slide. These fatty acids come in 2 different types. There are saturated fatty acids and there are unsaturated fatty acids. This is what I need you to know. A saturated fatty acid is a fatty acid that consists of all single bonded carbons. Look at the fatty acid illustrated at right. It's called saturated fatty acid there, and you'll notice all the carbons are single bonded to one another. Now, if all the carbons are single bonded to one another, what that means is you can have the maximum number of hydrogens surrounding those carbons in that chain. So if I look at the chain, I see all kinds of hydrogens. Every single carbon has 2 hydrogens bonded to it. That is a saturated fatty acid because it's saturated with hydrogens. It has the maximum number of hydrogens. And it happens to be linear. It's straight as an arrow. But now, in contrast, take a look at the unsaturated fatty acid that's illustrated immediately below that. And you will notice that an unsaturated fatty acid has a double bond in there. And that double bond does 2 things. Number one, it eliminates a couple of the hydrogens that we ordinarily would have. So if you look at the chain, you'll notice there is a gap where that double bond exists, and you don't have the full complement of hydrogens that you would. That's why it's called an unsaturated fatty acid, because it doesn't have the maximum number of hydrogens. But the second thing that the double bond does is it creates a bend in the fatty acid chain. And the difference between a straight fatty acid chain and a bent fatty acid chain is going to have everything to do with how, for example, a saturated triglyceride behaves versus an unsaturated triglyceride behaves. So let's go down to our next major point, which says fatty acids determine the molecule's property. If I take a look at a triglyceride, in my heart of hearts, I'm remembering that a triglyceride is composed of one molecule of glycerol and 3 fatty acids. But it's those fatty acids that are going to determine how the overall molecule behaves. Now, you'll remember that just a moment ago I said that fatty acids can be saturated or unsaturated, but I'm going to tell you this, triglycerides can be saturated or unsaturated also. See, when we apply the term saturated or unsaturated to a triglyceride, we're talking about a triglyceride that is composed of saturated or unsaturated fatty acids. So if you take a look at the couple illustrations on the right, at the bottom of the slide, and I'm looking at the one on the left, it says saturated fats. Saturated fats are saturated triglycerides. Those are triglycerides that are ultimately composed of saturated fatty acids. These are compounds that we commonly call fats. This is what I need you to know. I need you to know that fats, as a rule, are solid at room temperature. And the reason why they're solid at room temperature is because they're made up of those linear fatty acids. They pack very, very densely. And if they pack very, very densely, they tend to be solid at room temperature. This is the fat that you find under your arms. This is the fat you find in your belly. This is the fat you find on the edges of a piece of steak or a pork chop. Animal fat is solid at room temperature. It is a saturated triglyceride. It is composed of a glycerol molecule and 3 saturated fatty acids. In contrast, over there on the right, you'll see what appears to be an oil, like olive oil, like corn oil. Now, these are liquid at room temperature. They've got the same basic chemical composition. The only difference is that where a saturated triglyceride is composed of saturated fatty acids, an unsaturated triglyceride, an oil, is composed of unsaturated fatty acids. And because those unsaturated fatty acids are bent, they do not pack anywhere near as densely as the saturated triglyceride does, and therefore they tend to be liquid at room temperature. So you'll need to know that saturated triglycerides are fats. They're composed of saturated fatty acids. They're solid at room temperature. You'll need to know that unsaturated triglycerides, also known as oils, are liquid at room temperature. One more thing. The far majority of saturated triglycerides, the far majority of fats, come from animal sources. There are some exceptions, but the far majority of fats come from animals. And conversely, the far majority of unsaturated triglycerides, oils, come from plant sources. Once again, there are exceptions. And I can think of fish oil, for example, but by and large, the different triglyceride types, fats versus oils, not only sort out in terms of the chemical composition, not only sort out in terms of the way they behave at certain temperatures, they also sort out in terms of what organisms they're found in. And so you'll need to know that. All right, now we're going to talk about a second class of lipids called the phospholipids. They're really similar in composition to the triglycerides, They don't get as much press as the triglycerides, but in many ways they are the unsung heroes of biology because they are absolutely critical in terms of cell structure, and we'll mention that in a minute. In terms of composition, a phospholipid, a molecule of glycerol, bonded to two fatty acids, and instead of a third fatty acid, we're going to find a phosphate group. Now, the phosphate group has a charge on it. It's a negatively charged functional group, really. And so our phospholipid has literally two different personalities. On the list of items on the slide, you'll see composition, glycerol, two fatty acids, one phosphate, and then you'll see the word amphipathic. And it says this is a molecule with a split personality. The word amphipathic describes a molecule that has two different chemical natures. So what's the chemical nature? Well, if you take a look at the illustration of the chemical structure at right, and once again, I don't want you to memorize it, but you will see the two fatty acids, long chain molecules over there on the right, highlighted in light blue, and then you'll see the glycerol and the phosphate highlighted in a darker blue. When you've got a negative charge over there on the phosphates, that means that part of the molecule is polar. And if it's polar, that means it's attractive to water. So on the left, you'll see the dark blue rectangle. That's the head portion of the molecule. On the right, you see the two fatty acids. That's the tail portion of the molecule. As a matter of fact, if you want to see another version of it, look immediately below it on the left and you'll see a couple of renditions of what a phospholipid might look like. It looks like a head and two tails. And the head portion is polar, and therefore we're going to say the head portion is hydrophilic, and the tail portion is nonpolar, and we'll say that is hydrophobic. It's kind of like a Dr. Jekyll and Mr. Hyde kind of thing. And when this molecule occurs in water, it forms a bi-layered arrangement. And this is critical to its role in membrane structure. If you take a look at the far right bottom, you'll see a picture of a membrane in cross-section. And you'll see what looks like a lot of little blue balls. And those blue balls occur in two layers. And in between those layers, you see what looks like little yellow spaghettis. And if you look closely, you'll see that every single one of those blue balls has two yellow tails. And the blue balls and the yellow tails are phospholipids, and they are arranged in a bilayer. And that's how they always arrange themselves in water. So you will see bilayered arrangement in aqueous solution, which is nothing more than a $64,000 way of saying that these phospholipids arrange themselves in a bilayer when they occur in water. And the reason why they arrange themselves this way is that the head portions of the molecule, the little balls, are water-loving. And the tail portions, the little yellow squiggly things, are water-hating. And you can arrange yourself in such a way so that the head portions of the molecule are in close proximity to the water molecules, but in the bilayered arrangement, all the tails are found together in the middle of the bilayer where water is essentially excluded. The bottom line is a phospholipid arranges itself so it is most chemically comfortable in an aqueous solution. But the great thing is when it arranges itself that way, it forms the primary structure of a membrane. That could be a cell membrane that separates a cell from the environment outside of it. It could be a membrane surrounding an organelle. It could be a membrane found inside the cell that has a job to do. But the bottom line is that membrane would not exist if it were not for those phospholipids and their really, really unique structure and their really, really unique behavior. So make sure you know the structure of a phospholipid. Make sure you know what the word amphipathic means and know that they arrange themselves in this particular arrangement by virtue of the fact that the head portion of the molecule behaves much differently from the tail portion of the molecule. Our next type of lipid are the sterols. Sterols have no similarity with phospholipids or triglycerides, with the exception that they are nonpolar, that they are hydrophobic. So let's take a look. What are sterols? What are steroids? Well, these are molecules that all have a 4-fused hydrocarbon ring skeleton. Take a look at the chemical structure on the far upper right. Once again, it's not anything I want you to memorize, but you can recognize that. That is the basic structure of a sterol. Sterols have a number of different functions. They have a role to play in the stability of membranes. You see a number of phospholipids arranged in a bilayer over there, and you see some sterols embedded in the phospholipids. They have an awful lot to do with maintaining the stability of that membrane without going into a whole lot of detail. Sterols can function as hormones as well. At the bottom of our slide, kind of over to the left, you will see a series of what appear to be sterols, because they all have the same basic ring structure in different colors. I see a yellow one, I see a green one, a purple one, a red one. Those are all hormones, steroid hormones. Some of them are stress hormones, a couple of them are sex hormones, but those hormones are essentially important in terms of communicating messages in our bodies. And every single one of those hormones is derived from cholesterol. Cholesterol is our source molecule for all sterols in our body. And so you'll notice that cholesterol has that same basic 4-fused ring structure, as do all of these hormones. Cholesterol is a very, very important molecule. A lot of times it gets some bad press because, yes, we do identify negative health consequences for having too much cholesterol in your diet. But the fact of the matter is when you're a kid and you're developing, you need that cholesterol as your source molecule for building those hormones, in particular those sex hormones that are going to make you become reproductively mature. And then there's also vitamin D. I see vitamin D tucked in there on my list. And if I look over there on the far right, I see vitamin D, which incidentally is a vitamin that aids us in our ability to absorb calcium. And vitamin D has basically this standard sterol structure. Incidentally, vitamin D is made in our skin through the interaction of sunlight with cholesterol. You know, we really don't have to have a whole lot of vitamin D in our diets. If you spent enough time outside, you could generate enough vitamin D to serve your needs just through the interaction of sunlight with cholesterol in your skin. But sterols are a pretty important group, and despite the fact that they look a whole lot different from triglycerides and phospholipids, they still qualify as lipids. So, Dr. Canals, why are you mentioning fatty acids as a class of lipids? Because I thought you told me that fatty acids were a component of triglycerides and phospholipids. Well, they are. But the thing is I'm going to mention them now because they're extremely important in terms of our diet and some of the benefits that we get from them. So here's what I need you to know. Fatty acids are long hydrocarbon chains. Sometimes they're saturated, sometimes they're unsaturated. We already mentioned that fact. They do have an important role to play in our health quality. Now, in terms of fatty acids, there are two general types in our diet based on whether we're able to make them ourselves or not. You'll see non-essential fatty acids. These are the fatty acids that we can make all on our own. If we're missing a particular fatty acid, if it's a non-essential fatty acid, we can make it. But on the other hand, there are some fatty acids that we cannot make. And the fatty acids that we cannot make have to be present in our diet, and those are called essential fatty acids. And in many ways, the essential fatty acids are extremely important because they give us some very, very positive health benefits. There are two general types of essential fatty acids I need you to be aware of, and you've probably heard of these before. They're called omega-3 fatty acids and omega-6 fatty acids. The naming of the fatty acids has everything to do with where the double bond happens to be found. So it happens to be that these essential fatty acids are unsaturated fatty acids. And as a rule, unsaturated fatty acids are good for us. So you take a look at the illustration at right, and I notice that the double bond is illustrated there by a little red arrow, and it's indicating to me that in that molecule, the double bond appears to be 3 carbons from the end. That's why I'm going to call that omega-3 fatty acid. If it was omega-6, it would be 6 carbons from the end. But these essential fatty acids have an important role to play in the fact that they actually decrease inflammatory response. They actually have a role to play in making sure that your bad cholesterol levels, LDL levels in your blood are low. They'll help you improve your HDL, which is your good cholesterol levels. There's a number of good things that these fatty acids do. They're building blocks for making all kinds of hormone-like structures that improve our quality of life. Just a second ago, I mentioned hormones. Eicosanoids are a group of lipids that function as hormones. Our first bullet point tells me these are signaling molecules. They're hormones. What they do is they function as chemical messengers. And there's a number of them. They are all derived from those essential fatty acids I just mentioned. Probably one of the most important is a fatty acid called arachidonic acid. And arachidonic acid is a precursor to a lot of these hormone structures that we refer to as like eicosanoids, and they do a lot of different things. Now, in terms of the content on this slide, I just want you to practice name recognition. That's all. I am not going to ask you details of structure or anything else. I would never ask you to come up with these names. So if you see the name prostaglandin or you see the word leukotriene, don't worry about the details. Just know that prostaglandins and leukotrienes are eicosanoids. They are signaling molecules. They have a role to play in our biology. They do a whole lot of different things. They have a role to play in inflammation, in our perception of pain. They have roles to play in childbirth and labor. They have roles to play in regulating cell growth. They regulate blood pressure. They do a whole lot of different things. And, rather than memorize the chemical structures, just go look at them and you see, well, they look like long chain molecules. They look like fatty acids. Well, it's because they are. They just have very, very important roles to play, and they collectively get this name. They're called eicosanoids. Make sure you remember that. Let's talk about proteins. Start off by saying that arguably proteins are probably the most important of all of the biological molecules. Why would you say this, Dr. Knaus? Well, take a look at the very last bullet point on the slide. We're going to understand that our genes, the entire collection of genes that make us who we are, the genome, the collection of genes that make us human, encode instructions for making proteins. You've heard this before. And the proteins we make determine what we look like, how we function, and how we behave. Every single aspect of our biology, from the level of us as individuals all the way down to our individual cells, is ultimately controlled by the proteins that we make. They're ultimately encoded in the genes we got. So what makes these proteins so important otherwise? Well, first off, let's take a look at their general characteristics. I'm looking at a protein illustrated here on a slide. That's hemoglobin. Hemoglobin is a protein found in our red blood cells. You'll learn about it in great detail in AMP2. What hemoglobin does is it binds oxygen. Oxygen by itself is not soluble enough to dissolve in our bloodstream. We cannot transport oxygen in a dissolved form. Instead, what we do is we bind it to this protein called hemoglobin. It's almost like hemoglobin is like a seat in a taxi cab. And so oxygen gets in, buckles up, and takes a ride. And the taxi cab delivers oxygen to the cells that need it. So as a consequence, I'm able to transport enough oxygen to supply my needs, because if I had to rely on dissolved oxygen, I couldn't do it. But the bottom line, hemoglobin, like any other protein, is really, really big. Every single one of those balls on that picture there is an individual atom. So I've got all of these atoms arranged in all sorts of different ways, giving me this overall structure of this protein called hemoglobin. And it's different from every other protein. It's different in terms of its structure, and it's different in terms of what it does. So proteins are ultimately made up of individual molecules called amino acids. Even though that protein does not look like a long chain molecule, it is. It's all bunched up, but it is a long chain molecule, and those chains are composed of individual amino acids that are linked together by special bonds called peptide bonds. You'll need to know that. Now, amino acids are variable. We looked at amino acids not too long ago. I said, well, amino acid has got an amino group and it's got a carboxyl group, also known as an acid group, and that's where it gets its name. Well, amino acids are variable because they have different structures. In addition to the amino group and the carboxyl or acid group, there's another thing called a side chain that makes these molecules different. As a matter of fact, there's 20 different amino acids found in nature, and they vary based on that side chain. But the thing is with that degree of variability, when you put these amino acids together, the protein that you get can be highly, highly unique based on the variability in those amino acids. So what do proteins do? Well, they function as structural proteins. For example, our hair is protein, our fingernails are protein, the tough stuff in our outer layer of skin is protein, a lot of our bone tissue is protein, believe it or not, muscle tissue is protein. Proteins can also function as enzymes, the enzymes that break down the foods we eat, the enzymes that make things in our cells, the enzymes that transport things in our cells, the enzymes that do all sorts of things for us. And remember, what enzymes do is they lower activation energy. And I did mention the fact that I thought that 99.99% of all our reactions are carried out by enzymes. That's critical. Enzymes are proteins. And these proteins in our bodies, and it could be the proteins we have, could be the proteins we eat, they're not only going to provide us with calories, they're not only going to provide us with functions, but they're also going to provide us with the amino acids that we could need for building our own proteins. So proteins are very, very, very important. And we'll talk a little bit more detail about them in a moment. So what about these amino acids that make up these proteins? This is the case where you will need to know chemical structure. So if you take a look at upper right, you will see the structure of an amino acid. If you take a look at our list on the left, you will see those components identified there. You'll need to know this. An amino acid is a monomer component of a protein. When you link amino acids together, you get a chain. A chain of amino acids is called a polypeptide. The components of an amino acid are as follows. You've got a central carbon. On the left, I see an amino group, which is a nitrogen and 2 hydrogens. On the right, I see a carboxyl group, also known as an acid group, that consists of a carbon double bonded to an oxygen and a hydroxyl group. And then finally, there's a hydrogen in the 12 o'clock position, and then the mysterious side chain found in the 6 o'clock position. The side chain is the portion of the molecule that is variable. And I know they're really, really small, and this I do not want you to memorize, but that is the fact that every single one of those amino acids illustrated at the bottom right have the same basic structure as I see above. They just differ in terms of their side chains, and the side chains are highlighted in blue. Now, if you take a look at the additional picture there, you'll see a rectangle and you'll see 2 amino acids that are being linked together to form something called a peptide bond. A peptide bond is a linkage between 2 amino acids. Now, the thing is when you link 2 amino acids, you are going to carry out a condensation reaction. You'll remember that a condensation reaction, sometimes also called a dehydration synthesis reaction, is a reaction that creates a linkage between 2 monomers. Well, in this case, in the amino acid on the left, you see an OH group highlighted. You see a hydrogen on the amino group and the amino acid on the right. And if I remove the hydrogen and the OH group, that gets me a molecule of water. It also establishes a brand spanking new bond between those 2 amino acids. That is what I would call peptide bond formation. Now remember, it wasn't too long ago that I told you that proteins are highly variable and proteins are very unique. And their degree of variability and their degree of being unique has everything to do with the different amino acids that you can actually use to make a protein. You think about it, you're linking these amino acids together into chains or polypeptides, and you've got 20 different amino acids to choose from, and there's a multitude of different sequences you could possibly do. Multitude of sequences gives you a multitude of structures, gives you a multitude of possible functions that your protein could carry out. So proteins seem to be a lot more than just a handful of amino acids. Let's talk about protein structure. How do we take those amino acids and how do we get a big, fat, functional, 3-dimensional protein molecule? There are 4 different levels of protein structure you need to be aware of. Primary structure, secondary structure, tertiary structure, and quaternary structure. Now the thing is, if you don't like this illustration here, and there's going to be an illustration in your anatomy and physiology textbook, if you don't like those, just Google it. Google protein structure, click on images, and you will get 1,001 different versions of this content. And if you're like me, fact of the matter is not any one illustration will do. I mean, sometimes I've got to search until I find the illustration that does make sense to me. Sometimes I need multiple illustrations. Regardless, I'm a very visual person, and so what I see on the slide might not make sense unless I can visualize it. So let's take a look at the picture here. On the upper right of the illustration, you'll see a chain of balls of different colors. Those are amino acids, and those amino acids have different identities, and they are arranged in a particular sequence. That's what we call primary structure. It's the identity and sequence of amino acids in a polypeptide chain. Now, that polypeptide chain does not just sit there as a linear strand. It might coil, it might fold. And when it coils, that is called secondary structure. So immediately below that ball, that chain of balls there, you see what looks like a little coil. The chain of balls is really coiling up. That is secondary structure. Secondary structure is a coiling of the polypeptide chain. Secondary structure is a consequence of primary structure. Then we've got tertiary structure. If you take a look at the third illustration, which is kind of tucked over there on the right, you will see what looks to be a three-dimensional folding of this polypeptide. And then finally, we get to quaternary structures, which is where we actually get to the full functional protein. You see, when you take a look at primary structure, that's a feature of polypeptides. You look at secondary structure, that's a feature of polypeptides. If you look at tertiary structure, that's a feature of polypeptides. And a polypeptide is nothing more than a strand of amino acids. How is it that we can get to a protein? Well, that's where quaternary structure comes in. If you take a look at our illustration at right, you will see a folded arrangement of four, count them, four different polypeptides. One of them is red, one of them is orange-yellow, one of them is blue, one of them is green. That's actually a schematic view of a hemoglobin molecule. The same darn molecule we talked about not too long ago. See, a hemoglobin molecule is a composition of multiple polypeptides put together. And that's what all proteins are. They are a composition of multiple polypeptides, but when you put them together, they have a perfect structure, they have a perfect shape, and a perfect shape means they will have a perfect function. And really the thing is ultimately quaternary structure depends on tertiary structure, which depends on secondary structure, which ultimately depends on primary structure. You know, technically, all you have to do is change one amino acid and you could change every aspect of that protein, including the fact you could actually disable that protein and it won't work at all. And that could be catastrophic. So make sure that you know the four different levels of structure. And if you need to, Google it. Make sure you know that ultimately the shape of the protein is determined by its structure, and the shape of the protein is going to determine ultimately how it does its job. One very important aspect of proteins is the fact that you can, in fact, change their shape. Sometimes you can change it for the worse. Sometimes you can change it for better. We're going to talk about a topic here called denaturation. The official definition of denaturation is a negative change in protein structure. This is a term you will need to know. If you take a look at the illustration at right, you will see a coiled up protein that is being uncoiled in a process called denaturation. The uncoiled protein is essentially non-functional. What we're doing is we're performing a negative change in protein structure to the extent that the protein will not work anymore. Now, denaturation as an event can be permanent or it can be reversible. We give you an example of a permanent form of denaturation. Every single one of you have cooked eggs before, and you'll know that the egg, chicken egg, has got this goopy clear part that we call the white of the egg. Now, the reason why we call it the white of the egg is when you cook it, it becomes hard, white, and rubbery. That is actually a protein. It's a protein called albumin. And when you cook albumin, when you subject it to high temperature, it denatures. And that denaturation is manifested as a change in the consistency of the white of the egg. It becomes hard, it becomes white, it becomes rubbery, and in fact, it is an irreversible process. Now, in biology, a lot of times, denaturation is a highly controlled event, and what you can do is you can undo that structure just a little bit, just enough to negatively impact the function of the protein, but you can bring it back again. So what are the sorts of things that can actually trigger a denaturation event? Temperature, pH, salt concentration, enzymes can take that functional protein and render it unfunctional. But then we can always bring it back if it is a reversible process, and bringing it back is called renaturation, which would be a positive change in protein structure. And I should mention that denaturation and renaturation are a really good way of being able to regulate protein activity. If you got a protein that's doing too good a job, well, let's denature it a little bit. Let's turn it down. And if we need it again, well, let's change the structure and ramp it up. We'll renature it. So denaturation, renaturation are potentially reversible means of controlling protein activity based on controlling protein structure. Well, breathe a sigh of relief. Last category of organic compounds, and it's not going to take long. We're going to talk about nucleic acids. Nucleic acids are also polymers. They're long chain molecules, and they're long chains of individual units called nucleotides. Every single nucleotide consists of three things: a 5-carbon sugar, a phosphate group, and a nitrogenous base. In DNA, which is the genetic code, the 5-carbon sugar is called deoxyribose. In RNA, which has a role to play in protein synthesis, which we'll talk about when we get to the presentation on cells, the 5-carbon sugar is called ribose. That's why DNA has its first letter as D for deoxyribose, and RNA has R as its first letter for ribose. Well, there's something else about these nucleotides, and it's pretty critical. These nucleotides have a nitrogenous base, and the nitrogenous base in the illustration over yonder is that 2 green ring structure. The 5-carbon sugar is the pentagon, the phosphate is the blue circle, and the green shapes is basically the nitrogenous base. Well, nitrogenous bases are variable. They come in 4 different types in DNA. One is called adenine, it's abbreviated A. One is called cytosine, it's abbreviated C. One is called guanine, it's abbreviated G. And one is called thymine, it's abbreviated T. Now, it happens to be that RNA will have the exact same nucleotides, except for one. Instead of having thymine, RNA will replace that with a nucleotide called uracil. Otherwise, they're pretty much the same in terms of their composition. There's some differences in terms of structure, but they both demonstrate some variability in the form of these different nucleotides. DNA has A, C, G, and T, and RNA has A, C, G, and U. Well, let's take a look at the structure of DNA. DNA is commonly referred to as the double helix, which is kind of a descriptor. It is a helical molecule, which means it's kind of spiral shaped, but it's 2 strands spiraling around one another, almost like if you took a ladder and twisted it on itself. So the rails of the ladder, the vertical portions that are parallel, are sugar phosphate strands. And between the sugar phosphate strands, I've got base pairs. The nitrogenous bases, you'll remember, are going to be paired across that interstrand distance. So technically, if you look at the illustration at right, you will see a series of nucleotides joined together on the left. You'll see a series of nucleotides joined together on the right. And the strand on the left is sugar bonded to phosphate, bonded to sugar, bonded to phosphate, and the strand on the right is the same way. and the nitrogenous bases are paired across the middle. Now, those nitrogenous bases occur in what we call complementary base pairs because they're very specific. A always pairs with T, T always pairs with A, C with G, and G with C. Well, you'll notice something. A is a 2-ring nitrogenous base. T is a 1-ring nitrogenous base. Well, G is a 2-ring nitrogenous base, and C is a 1-ring nitrogenous base. In other words, when you get these complementary pairs, it's always a big one paired with a small one. And that means you will always have an equivalent interstrand distance, regardless of what nitrogenous base pair you have. And so the two sugar phosphate strands are going to be parallel to one another. Of the two strands making up the DNA molecule, one strand is called the template strand. That template strand contains the critical information necessary to make the protein. The other strand is not so important. It is referred to as a coding strand. What holds those two strands together, however, or more specifically, what holds the complementary base pairs together, are hydrogen bonds that form between the two nitrogenous bases. The DNA is located in the nucleus. The nucleus is the genetic library of the cell, and it's a permanent repository for that information. And the DNA in the nucleus is generally packaged with protein, and the combination of DNA and protein is called chromatin. It's where we get the name chromosome. So DNA is the molecule that contains our genetic code, all the encoded information for what makes us humans, our human genome, and the individual genes are sequences of DNA that code for the proteins that make us who we are as humans, but make us who we are as individuals and govern every single aspect of our biology, both inside and out. So let's turn our attention from DNA to RNA. RNA is different. It's got a single-stranded structure. It's not a double-stranded molecule. And the single strand is a sugar phosphate strand, just like it is in DNA, but we've got a different selection of nitrogenous bases. You'll remember that A, C, and G are also nitrogenous bases in the DNA molecule, but in RNA, instead of having T, the thymine, we're going to replace it with U, or uracil. Now, whereas DNA is a permanent record of our genetic information, and it's always there in our nuclei, RNA is a much more transient molecule. We're going to make it as needed. If you take a look at our illustration on this slide, you will see a cell. And in the upper left, you'll see a big round shape, which is the nucleus. And you'll see a bunch of stuff going on. What I see going on is we're going to take the DNA molecule, which is illustrated up there in the upper left. We're going to unzip it, and we're going to make a copy. And the copy of that DNA strand is called mRNA. mRNA, little m, stands for messenger. We're going to take the message contained in the DNA molecule that we copied, and we're going to move it into the cytoplasm. And once we're out in the cytoplasm, what we're going to do is going to read that mRNA molecule. And if you take a look at the illustration, you'll see a big shape that seems to be moving along the mRNA molecule from left to right. That's a ribosome. And a ribosome is made out of RNA. Specifically, it's called rRNA. And its job is to read the sequence on the mRNA molecule. And as it does so, it's going to assemble amino acids into a protein. I need something to bring those amino acids to the ribosome. And that something is another molecule of RNA called tRNA. The little t stands for transfer. And you'll see what looks like little T-shaped molecules bringing amino acids to the ribosome and dropping them off. So whereas the DNA molecule is a permanent record of what we need to do to build the protein, RNA is going to appear as needed to either copy the DNA molecule, generate ribosomes to read the mRNA molecule, or the tRNA molecules to carry the amino acids to the ribosome as we're building the protein. So what you're going to need to do is to make sure you know what DNA is and the role it plays, what RNA is and the role it plays, and more specifically, I need you to know the identities of those RNA molecules that you see down there on this slide. And it's going to be something that you're going to bump into when we get into the presentation on cells not too long from now. Last but not least, we're going to wrap up this discussion about nucleic acids by talking about one other very important nucleic acid-like compound. It's not really a nucleic acid because it's not a polymer. It's more like a nucleotide, and it's this thing that we had mentioned before. It's called ATP. You will need to know that ATP stands for adenosine triphosphate. It's a nucleotide, and it's got 3 phosphate groups bonded to what essentially is an adenine. Those phosphates are linked together by bonds. And of those bonds, the bond to the 3rd phosphate is the most important because it is a high energy bond. It contains a tremendous amount of energy. That ATP molecule is like cellular gasoline. It's cellular fuel. It is the energy currency of the cell. It's universally usable, and it is immediately usable if I need to do something in the cell. And it's an energy-intensive process. And it doesn't matter whether it's making something or breaking something or moving something or transforming something. I can extract energy from the ATP molecule and get it done. And the way I do that is by removing that high energy phosphate group. So if I think about ATP, if I can break ATP, I certainly can make it. So the reactions involved in making and breaking ATP are part of what we call the ATP cycle. And you'll see it illustrated there in the lower right-hand side of the slide. And the ATP cycle involves a process of making ATP and breaking ATP. Making ATP is called phosphorylation. Don't let your eyes roll back in your head. The word phosphorylation is a $64,000 word meaning adding phosphate to something. So if you take a look at the illustration at 6 o'clock on the illustration, down towards the bottom, you'll see ADP. That's adenosine diphosphate. You'll see 2 little phosphates there. As you move to 9 o'clock, you will see what we're going to do is going to add a phosphate group. We're going to add a whole bunch of energy, and that's going to add the 3rd phosphate. That makes a high energy ATP molecule. Then when time comes, I need that energy. I'm going to break the ATP molecule, and that process is called hydrolysis. We've seen that term before. To do the hydrolysis of ATP, all I have to do is cleave the bond to the 3rd phosphate, release the energy, and I can get work done. But I'm right back to ADP again. So the ATP cycle is nothing more than a process of phosphorylation, hydrolysis, phosphorylation, hydrolysis, making, breaking. This is how we take the energy from, for example, a food molecule and use it to make ATP, and then we take the energy out in order to do something like maybe contract a muscle or something like that. So make sure you know what is ATP, make sure you know what is the ATP cycle, and what those 2 components of that cycle are.